To explain digital audio, we need to understand what analog audio is, so we can contrast it. And they're both, you can't really have digital audio without a certain amount of analog audio as well, which we'll come to that later. But let's try to understand how the speaker works first. We've all seen a speaker, so this is probably a good place to start. So we're familiar with this part here. It's cut away, obviously, and you have a cone shape. This pushes the air in the room, which creates the sound. That's in a suspension. And there's a coil of wire around this central piston, which moves up and down inside a magnet. Now, there's an electrical current that feeds this coil, and that electrical current uses electromagnetism, which we'll explain in a minute, to move the cone in and out. Now, we just need to have a look at sound for a second. Now, sound doesn't travel in this up and down wave. It travels, that's a longitudinal wave. It travels in a transverse wave. So this is another way, better way of looking at it. If this is the speaker diaphragm, or the cone, and that's moving out, as it moves out, it pushes all the air molecules close together, and this wave of dense air molecules travels across the room. Now, the molecules themselves stay put, but it's a bit like a car crash involving lots of different cars. The back car hits it into the one in front of that hits into the one in front of that, and so on. And the shock wave of the crash travels along all the cars in a queue. And it's the same with the air molecules. They all box off each other, and the energy travels the room, but the molecules stay where they are. So this dark line here is where the density of the air molecules is at its highest. And that also is represented then by the highest peak on this graph here, this waveform graph that we're used to looking at. Now, there's another kind of point where in between the two of these, where the air is at its least dense point, and that's represented by the lowest point on the graph. Now, at a different frequency, you can see that the speed of sound is the same, but the speaker is moving faster to create more of these pulses. So the frequency is faster. Now, the amount that these particles are moving are the same. You see the height of the wave is the same, and that's the amplitude. The amplitude is the same. Okay, so this is a screen grab from Ableton. Now you can see there's lots of different amplitudes, which is the height above the middle line, or I want to call it, for want of a better word, the height below the line, but just the distance away from this line is the amplitude. And how quickly this wave changes back and forwards on the line is the frequency. And you might remember, the higher the frequency, the higher the sound. The lower the frequency, the lower, bassier the sound will be. Now, you could think of this diagram as a chart of how the speaker cone has to move to create this sound. So the speaker cone will be at rest when it's at the line. It'll be extended forward when it moves above the line. And it'll move in an exact trace of this line here over time. As time goes onwards, this is the amount it'll move from the center position until the signal is no longer sent to it. At that point, it'll just be a straight line along. If you were to track the movement of the speaker cone in and out over time, it would have the same shape, waveform, as if you were to track a single air molecule that was vibrating in the air from that sound. And if you were to track the change in electrical current going to the speaker, it would have the same amplitude, positive and negative, and the same frequencies as the sound, as the movement of the speaker, as the movement back and forth, the oscillation of the molecules of air. Now, some of you might be worried we're straying far into the realm of science here, but this is just to help you understand the connection between electricity and magnetism. So we're going to delve a little bit into electromagnetism. And this is going to help the other information make sense. Electromagnetism, bear with me. You may have done this experiment in school where you get, let's say you have your battery. Now, batteries have plus and minus connectors on them. Here's our battery. And if you have, say, a nail, there's our nail. And if you take a wire from the battery and wrap it around the nail, so that's just coiling in around the nail. There it comes out the other side. Now, so that's attached here and here, and it's wrapping around the nail. What happens is the nail becomes magnetized. So it ends up with two poles, a south pole and a north pole. And you get this magnetic field. I don't know if you remember drawing magnetic fields, but it's something like this. So electricity creates magnetism. There was another version of this where instead of putting a nail, you put something hollow. Like imagine if this is a hollow piece of a straw, and then you wrap the wire around it. You know, this creates this magnetic field. And what happens now, we thought was quite cool, was that if you got something like a pin and put it in this side, it would travel from the south end to the north end and it would just fly out the other side. So you'd have this pin and it would just hover in the middle of the tube and be ejected the other side if the magnet was strong enough. So if you're into science fiction, I was, like, you'd be thinking, wow, this is how they'd make levitating trains. They'd have things in a magnetic field suspended. Or you could make some sort of a weapon where you would, with the strength of the magnetic field, you'd be able to propel things from one side to the other. And that's where they get the idea of rail guns. I'm sure that's popped up on one of your games, but that's how they work. It's the strength of the magnetic field